projection, right? So we have some kind of funny foreground here. This is this little bunny here, which dances in front of the canvas. And this foreground or this forward mapping can be done quite easily, but then reverting it is very difficult, right? So the inverse mapping of that from the shadow to the 3D object, this is very difficult with standard model-based approaches, right? If you just want to have a physical model of that and reproject it, then this wouldn't be very, very easy. And this is also true for other problems, right? So for example, for object classification, for 3D reconstruction, these are also so-called inverse problems, and that makes it very difficult to actually solve. Now the idea is, why can't we also do the same thing as we do as humans, right? Humans use a lot of experience, right? They have seen certain things already a number of times, and you can think of this as kind of data, right, that they collect, and this data, should be kind of useful to actually be able to reconstruct this kind of scene, right? So from the 2D viewpoint to a 3D point. So this is the key idea of why we use data-driven or learning methods to solve these kind of inverse problems, right? This is the major idea here. So use data-driven approaches to fill this kind of information gap. And as a small teaser, I'd also like to show you how we solve this. In particular, this kind of problem is actually solved in this work here. This was a work that we did 2 years ago at ECCV, where we reconstruct scenes from single views, right? So this is exactly what this kind of example has shown you before. So on the left, you see images that were just simple molecular images generated from a real data set, right? We've generated views from the replica data set. And we also have these normal vectors, which is the small images below that. And from that, you can train a network that can reconstruct the scene just from this one single view. And the key idea is that, of course, you have a clever network that needs to be able to represent the 3D space, which is one part. But the other part is that you need a lot of training data that you can use, that you can generate from synthetic images, right? You can simulate all these images and then train a very large network to actually learn how things might look like. And yeah, you see this here on in the middle. The middle column is actually the ground truth, right? And the right one is our predictions. And these kind of reddish pink areas, these are areas where you wouldn't see, right? This is the occlusion areas where in the 2D image you can't see because the 3D area is occluded. But still, the method is able to kind of hallucinate that because it has learned that things look like that in general, right? So this is the main message here. Okay, so that's nice, but then coming back to the discussion of data-driven versus model-based. So in general, there is these kind of two kind of approaches. And the classical way is this so-called model-based approach where we have a physical model and we have, again, some data as well, but then we use that kind of data to kind of optimize parameters in this physical model. This is an example of a light field camera, plan of the camera where we have a lens here and then many lenses here and all kinds of physical parameters here, right? So it's a more complicated model than a standard camera. But it can be modeled physically quite well, right? And this is a typical example of a model-based approach where we have a physical model, we know exactly how to describe the world, and all we need is find parameters of these models here, right? So calibrate this camera, the intrinsics of this camera, and how we do this is we use, of course, calibration patterns, and then we run our optimization algorithm, and that's it. Now, compared to that, learning is very similar, right? It has a very similar idea. However, it has also quite some differences. And the major difference is that, first of all, the input data that we use here, the training data, is much larger, right? And much more diverse, right? So it's like lots of different kind of images. It could be, anything that you could think of. And we'll see later also examples that the more diverse the data, the better. And the larger the data, also the better. Then you also have some kind of model, but this model is not exactly the same as a physical model. It's a more general model. It's just a function, right? A mathematical function that has parameters. And in this case here, you see this autoencoder here, right? It's just one way of describing that, but mathematically, it's nothing else than a big function with many, many parameters. And the big difference here is that those parameters, they cannot be linked physically to any physical units, right? You cannot have lengths or weights or anything like that, any units, any physical units for these parameters, right? And then, of course, you do also optimization, but not only that, because the optimization step is just one part of learning. The other part is, of course, the predictions and the inference. So that means you want to actually be able to infer new things in new data sets. Now, the question is, what is the better approach? And in general, of course, it's hard to say that. Many problems so far, and more and more problems so far, are actually being addressed with learning and with data-driven approaches. And there's a very promising direction of that. But it doesn't mean that we have to do this always, right? Here, I just show you some examples where it's probably not so useful or not so necessary to do learning. For example, camera calibration, robot motion, and these kind of things. We also have examples which I don't show today on object tracking, which you can do very quickly, very fast in, I don't know, thousands of frames per second without any learning, right? Just have a very precise physical model and you can it's much better. So this brings me to the kind of discussion, what is better? Well, we have model-based, we have data-driven. Model-based approaches require an abstract physical model that I said already. The advantages, of course, are precision and speed. So if you have a good physical model, then they're very precise and very fast, right? Then you can use them very quickly. However, of course, transferability is not so easy, right? So transfer one, for example, in this camera here, if you have another camera and you need another model, right? So it's not so easy to transfer that. And also, as I showed you already, these inverse problems are not so easy to solve with these classical model-based approaches. And the data-driven approaches, they are in general very useful whenever you have some features, right? Whenever you have some image input and you want to extract some features that you then match or whatever, then data-driven approaches are much better. Their advantage is that they generalize much better to new situations. However, and that's the big disadvantage, which I'm going to try to cope with today, they need training, right? They need training data and they need training phases. They need a lot of hardware, a lot of time to do the training. And also we need ground truth data, right? This is an important thing as well. So for now, we are talking about data-driven methods. And I told you already that when we do data-driven approaches, then we have to face at least these three kind of challenges. And these kind of three challenges are also kind of the outline of my talk. So the first major challenge that we face is that we need very good training data, and not good, but also large training data sets, right? So the bigger, the better, right? In large networks. And also, of course, the ground truth must be reliable. We need good ground truth labels for our training process. The second major challenge that we face is in these systems that we have in these real world systems like robotics and others. Very often it's not sufficient to just have a prediction, right? It's not okay to just say, well, this is object A or B, but also we need some kind of confidence, some kind of estimate of the system that tells us how likely is it that this prediction is actually the correct one, right? How much can I trust on that prediction? Because in the end, I have to take decisions that are based on that prediction, right? So if I predict a pedestrian or a car, whatever, then the self-driving car actually should do some kind of action that reacts on that, right? And so that means that the prediction I do here is very important and safety critical, right? And for that reason, I need a good uncertainty estimate as well. And then a typical problem is that data-driven predictors, so for example, classifiers or regressors, they tend to be overconfident in general, right? And that is a problem in general with especially deep neural networks. And the last problem here is that, especially in robotics, but also in autonomous driving and other applications, we need to be very efficient in terms of the resources, which means we have to be fast in the inference, but we also have only very limited hardware where we can actually run this on, right? So we have embedded GPU or something like that. We don't have big computers on the robots or any other, also on the cars or any other mobile systems where we cannot really make sure that we have good computational power. So I'm going now through this step by step. I'm showing you the first kind of challenge and how we can address that. So this is an example that I'd like to show in my class here. This is from the regression class that I show. The message here is that large models require large training data. And this is shown here in the upper three images here. So this is just a toy example, of course, but it shows nicely what happens if you have too many parameters in your model, right? So if you have 10 data points and you fit a polynomial in those 10 data points with a degree of 5, then you have a smooth blue curve here, which is the estimate, right? The red one is the true data, and the green dots are the sample data. Of course, it's artificial data, but it's just with some Gaussian noise. And you see that this model works quite nicely. However, now if you increase the number of model parameters, in this case, model parameters are just degrees of this polynomial, then you have a complete overshoot here, right? So between the data points, we have a complete overfitting, and that means that the model is not well suited to do predictions between the data points, right? So if you want to say, what's the sample between this and this data point, then it will be completely different from the ground truth. And that's because we have no fitting situation. And one way of addressing that, in this case, it's easy. Well, we just sample more data, right? So this is just 10 times more data. And with the same number of parameters, 10 parameters here, we'll still have a good smooth model, right? And this is the message. So the bigger the parameters is, the more data we need. However, in reality, we can't do this because in reality, we just have a given data set and we cannot just sample more. And for that, there are many different approaches to address that. One important thing is regularization, right? So the big networks are all regularized, of course, otherwise it wouldn't be possible. You use, of course, data augmentation, right? To generate or produce more data without actually having to label it. However, what I'm also showing today here is some other alternatives. And one important and interesting alternative is using synthetic training data, right? Which again, does the same thing as here. It produces more data samples without actually having to label them, right? We don't actually need a ground truth for that. This was impressively shown in the BOP challenge, in the benchmark on object pose estimation at ECCV 2020, where the winner approach by Labé et al. Called Cozy Pose, they showed with a very clever training process where they used real images, right, TLS and ICB, but in addition to that, they also used 1 million synthetically rendered images. And these are shown like here. So these are very, very diverse and different from what you actually have in the real scene, right? You would really think that this wouldn't be even close to what the scene actually does here. But this was also key, right? They also showed in their paper that it's really good to have this kind of diversity in your training data, right? And with that, they actually won the challenge here with finding the 60 pose in this scene here. And another alternative to do this is self-supervised training, and I'm also showing some example how to do that. So now let's show you some examples of how we in my group use and produce synthetic training data. We have two tools where we actually use that for, and both are based on Blender. Blender is a rendering software that can produce photorealistic images. I'm showing you the video here of Blender Proc version 2. This was developed by my colleague Max Denninger. So here, the whole idea is that you have a pipeline of different tools to produce scenes, but also to produce things like semantic segmentation and so on, right? So you have, in the end, of course, Blender is the workhorse basically and builds these scenes here. But before you can use Blender, you have to do a lot of pre-calculations and pre-processings. And these are done very simply and easily with this Blender Proc. Blender Proc is available on GitHub. You can just download it and have a look. It's quite famous. I think it has already like 1,000 stars, something like that. So quite a lot of views already. I think it's quite used a lot in the community, and invite you to use that. And you see also that we have some physics simulation with objects, right? You can throw objects into the scene and then they would lie in a certain where they fall. The second example is Oasis. This is this example here on the right, which is also based on Blender, but now this is for outdoor scenes. So here we have basically a ground simulation with different textures, again, also with physically based rendering textures, and also photorealistic, of course. But in addition, we also add certain objects like rocks, stones, but also plants we can add. And all these kind of things. So this is our, say, tool framework for generating outdoor synthetic training data. Again, this is also available on GitHub. Here you see it's an easy configuration file. You can add, as I said, trees and plants and whatever. But importantly, you have these kind of semantics, right? You can have several layers of semantics and also instance annotations. Okay, now that we have this nice stream data or synthetic data, what can we do with it? And I'd like to show you some examples of how we can use synthetic training data to do to solve perception tasks in robotics, but not, right? So here, this is an example of how we train a network to segment unknown objects in a scene, right? So you have these kind of scenes here, and the network learns to find objects without actually knowing the name of these objects, right? It's not really a classification, it's just telling that this contour here around this object should be the segmentation to find that this is the object from the foreground, right? So we assume, of course, we have some kind of planar surface, which is this table here. But then once we have that, we can find all these objects with this method. And the key idea is here to use stereo input, right? We have two images which are slightly different viewpoint. And the network learns how from this kind of two views, we can do the segmentation here. We use a recent framework here. It's called detection transformer, right? These are transformers, which are not standard CNNs, but slightly different architecture here, which comes from the natural language processing domain. We also have this auxiliary task here to train a disparity decoder, right? So this is also important, which showed also better results here. However, I stress that we don't actually do this disparity first and reproduce the 3D point cloud from that and then do the instant segmentation, but we do this directly, right? So we directly run from the input pairs how to segment the input images. And that turned out to be better than classical approaches where you first have 3D reconstruction from the stereo images, and then from the reconstruction you do the instant segmentation. So this is a video of how this looks like. This is just some random objects that are on the table, on the chair, and on the floor. And note important here is that these objects have not been seen in the training data. And what I have forgotten to tell you that, of course, is that the whole network is completely trained in simulation, right? We have not taken any real image on that. We have not labeled by hand any objects or anything like that. We produce with Blender a very large set of training images, right? And only for this kind of data we learn how the objects can be segmented. And you see that this kind of wiggles around, so we have different labels across the frames because we don't do tracking, right? It's just frame by frame, and in every frame we just segment out the objects from the ground. A second example where we also leverage a lot of synthetic training data is this one here. So here, the aim is to learn a grasp from a given object, right? So we are given this gripper here. This is a typical robotic gripper with 2 fingers here. And the aim is to, at a given object here, to find the grasp such that the object doesn't fall off, right? And again, one important problem here is the representation. So how can we represent these 6 degrees of freedom of this gripper here, right? So this is, of course, a dimensionality problem. And in this case, the PhD student Martin Sundermeier found a very nice efficient representation to kind of project the 6 degrees of freedom of the gripper onto the point cloud of these objects, right? So basically what you do is you classify points in the point cloud as suitable contact points and unsuitable contact points. And suitable means that if I place the gripper on those points, then it will very likely have a stable grasp. And if I put the gripper on the unsuitable contact points, then very likely I will not have a grasp, then the object will fall off. So yeah, this is the key insight behind it. We have this kind of grasp net, contact grasp net, that we developed here. Here we have the depth image and the camera image. But again, important is that we train this with some simulated data. And for that, there's a special kind of data set called acronym. It's a very funny name for a data set. It's actually an acronym, so it's called acronym. And it consists of almost 9,000 meshes of objects. And in addition to that, there are over 17.7 million different grasps in that data set, right? Again, a simulated data set, not synthetic data set, right? So you do as if you grasp the objects in simulation all the time, 17 million times. And from that, you learn how objects can be grasped, right? And the result is something like that, where we have a point cloud. And in the point cloud, you have per object stable grasps, right? There's a lot of candidate grasps. And then always one is the best one, which is this thicker one here, right? And that means that this will be the one that robot will try next, right? So in combination with the instant segmentation that I just showed you before, right? This is again the network that, or a similar network to what I showed before, where we have an input image and we segment out the different objects. In combination with the grasp, we can then say which object has to be grasped at which position. And this is the result here. This is, again, these objects are not known to the robot, right? They're not trained. It's all on trained simulation. And you see that the success rate is very high, right? So over 90% of grasp performance. So only very little times the grasp is not successful. And in this video, you see that it can actually grasp all the objects without actually having seen them before. And in the scene, of course, it's kind of still easy because these objects are separated from each other, right? They stand more or less alone, one from the other one. Then we did another example where we did this in our lab here, where we use our robot, and now the objects are not separated. Now they're like piled. And you can see on the right, the two images that the robot sees, right? This is the segmentation image where it uses our instant segmentation to really find the objects, right? And in the lower right, let me just start the video again. In the lower right, you see the candidate grasps, right? You see where the robot is supposed to grasp next. And interestingly, the first grasp is actually this object, which sits below the other object, the banana here, right? But it doesn't actually care about this. It's just like a child that tries to grasp the best thing. Let's take that one. And then of course, then the banana will be moved and our other object will be also moved. But that's okay because the robot actually doesn't know about these objects, right? It just knows about grasps, right? It just learns by, or interacts with the scene and then uses this grasping to be able to separate the objects as well. Okay. Another example I'd like to show is in the context of terrain classification. So this is clearly, of course, an outdoor application, which is, of course, also important for robotics, but not only. Here, what we use is our OASIS simulation. These are just some examples of images that we created with OASIS. And then what we did is we trained a standard network, in this case, DeepLab version 3, to segment terrain types, right? We have, in this case, 5 classes here, right? Well, sky is not really a terrain type, but the other ones are. And that we applied to a real data set that we actually acquired in Morocco. So these images here are from the desert of Morocco. The point there is that it looks very Mars-like, so it's really reddish, and the data is like very similar to a Mars kind of environment. And for that reason, we went there and took some data there. And yeah, of course, the ground truth is made by hand here, but you can see that the prediction that we can learn from this simply simulated training data is quite accurate, right? So it's probably looks even in this image is better than, of course, in the numbers, but of course the numbers are always more important. That's right. Dried mud is a class that is not so easy to classify, but the other classes are quite good. Okay, and this is shown here in this in our IRIS paper from last year. And this is another example where we can use also inster. So we said, well, now we have a method that can segment objects, unknown objects from flat background. Can we not also use that same also in this outdoor scenario? And if we did that, and we found out, yes, we can do that. So in the top row, we see 3 example images of stones that were scattered around different backgrounds. And the straightforward inster method, which was trained only on in-draw objects, right, in simulation, it did quite a good job already. However, as you see here, these red areas here, those are errors, right? There, the insta segmentation was not good because it actually has never seen these kind of stones, right? It was never trained on those. However, what we can do now is we can fine tune it on our OASIS data, which is again also in simulation, right? And then we see that the insta segmentation works much better. And we can also show that this works in real time. So we have demos where we show this rock segmentation just directly from in real time. And this was also part of this paper here. Yeah, so this was all about synthetic training data. But then there's also another interesting aspect, and very often you don't have the synthetic training data, right? You cannot just synthesize everything. And this is an example where we use some other techniques. It's a master thesis that I supervised at the Solar Research Institute of DLR. There they have the aim to classify so-called all-sky images, right? This is what I showed before already. We have some input images here. And for example, you want to, first of all, classify the kind of clouds. You want to also predict where the clouds move then. Of course, for the solar power plant, it's very important to know when clouds come and where the clouds are, because then you might be able to direct your mirrors in a certain different way so that you are not hidden by the clouds. So these are the ideas behind that. And yeah, here we also used a deep learning framework. We used this UNet with ResNet34 backbone. But again, we had the issue of getting a large training data set. And what we found out is that so-called self-supervised learning framework is actually quite a good idea. It actually improved the result quite significantly. Here, this is what this looks like. So we have actually one initial image, which is just a standard cloud image, which is basically called the ground truth. And what we do now is we mask out a black box here, right? This black box is just overlaid onto the original image here, right? And then we train the network to refill this gap again, right? So we say, this is the input, this is the output, and we train this network here. And the network then learns to fill this gap. And you see here that this is the result, right? This is the prediction. It's not exactly as the ground truth, but it's quite good already, right? You can say, well, there's a quite good understanding of the environment. It didn't do such a bad job on actually refilling that gap here. And the interesting thing is that this kind of, it's called a pretext task, right? We do this first with our network. We train this network first, and then we train it to segment these objects here, and we can show that this works much better, right? So the idea behind this, or the motivation, is that the network has then learned how to deal with these cloudy images, and then can use it to actually do the segmentation here. Okay, so far about quality and amount of training data. Now I'm coming to the second point of my talk, which is predictive uncertainty. So how can we, first of all, estimate uncertainty, and how can we build models that know about their predictions better in terms of uncertainty? Before I go there, I'd like to first understand what are the different kind of sources of uncertainty. And there are basically three kinds of different sources where uncertainty comes from. And this is shown here in these three different columns here, one for the regression case and one for the classification case. This is from a recent paper that we did together also in the group here with a large number of authors, which I think is quite a nice work, where we have a survey over different uncertainty methods. The first author, Jakub Klawikowski, is also, I think, here. So this is a very nice visualization of showing what happens, for example, in the case of data uncertainty, right? You might have a ground truth that is this one here, or the underlying data generator. And then, for example, noise in the data can cause a high data uncertainty, which is here. And in the other case here, below here, there's a lower uncertainty in the data. Now, even if you have a perfect data without any noise, you still have sometimes some uncertainty, and this comes from the model, right? Because if you now train models on this kind of data, you will not always have exactly the same model that comes out of that, right? Because there's some randomness in the learning process, and you will have different kind of models that are learned from this kind of training data. And that means if you learn different kind of models, they can differ quite significantly in their predictions right, in certain areas of the training data. So here you have a higher distance between two models, right, a higher disagreement between the two models than you have it here, right? And this again causes uncertainty, of course, right? Because that doesn't let you exactly specify what's the correct prediction here. Because if the models disagree, then you would not be able to actually predict the good value here. And the third kind of uncertainty is distributional uncertainty. This is this one here. This mainly is visible in so-called out-of-distribution areas, right? So where you are far away from the training data, there what happens often is that the models that you train, they disagree as well, right? So this is very similar to here, right? However, it's now really more like precisely shown that even if the models agree on the training data, they can still disagree a lot away from the training data, right? And this again causes, of course, uncertainty. Now, for the classification, you have the same situation. We have data uncertainty where you have, for example, overlapping classes, right? This is confusions, right? You have data points that look similar but are different classes. This confuses, of course, the classifier. And here you have the situation where we have low model uncertainty in here, but then a higher model uncertainty in this area here, where because the two models, they separate the two classes quite differently, and that is the same situation as here, right? So you don't know which model to actually use because both separate the data well, but then away from data here you have some uncertainty. And of course, the typical example of order of distribution samples is here. If you have a new class that is taken from out of the training data set, which also causes then uncertainty. Now, if you know now what uncertainty is, the next question is how can we tackle it and how can we build methods that actually give good uncertainty estimates. And there's many different approaches to do that. I'm not going to the overview of that. Again, I'm referring to the paper where we show all the different techniques to actually address uncertainty estimations. I'd like to just show you one example here, which is the so-called Bayesian neural network, right? The Bayesian neural network, what does it mean? Well, we have a standard deep network. Here is just depicted as some convolutional layers and some fully connected layers here, right? So this is just a very rough sketch here of how a network might look like. Of course, for every layer, you have inputs, you have the pre-activations here, the H1s, H2, and so on. And you have, of course, the activation functions that are applied to the pre-activations, right? In the end, if in this case, it's a classification, then we have a softmax layer in the end, and you use the so-called cross-entry loss function to train this network, right? This is the standard way of doing learning with a classifier. Now, how do we turn this standard network into a Bayesian neural network? Well, the idea is that the weights that are learned in this kind of network, they are not just single values that are optimized, but instead we have a distribution over these kind of weights, right? So here, this is shown in this figure here. So this is the log likelihood function, which we actually have to optimize. Note that it's not a negative log likelihood because it's nicer to visualize. So we want to maximize that one in theory, or actually what we have is the negative log likelihood, which is what we have to minimize. So in this case, you assume that we have a maximum of this log likelihood function, which is the standard output of our training process, right? This is the set of parameters that maximizes our likelihood. But now, instead of just using this one value here, this one maximum value, we are using a distribution around that value, right? And distribution is, in our case, Gaussian, right? We use a Gaussian distribution that has this mu w, this maximum likelihood value, as a mean value, and it also needs a covariance matrix. And we use the covariance matrix that is approximately the inverse of the Hessian of the log likelihood, or the negative log likelihood, actually, right? So here, intuitively, this means that the curvature of this optimization function that we have, this curvature tells us about the uncertainty of our estimation. So it tells us if the curvature is very high, then we have a higher. Sorry, if the curvature is high, then we have a lower uncertainty. That means we have a peaked Gaussian. And if we have a flat area where the curvature is low, then we have also a flat covariance, meaning that we have a higher uncertainty, right? Okay, this is the theory behind it. This is the idea how to use it, which means at the end we have a big long vector here and a big, even bigger matrix, because now the vector is as long as we have parameters in the network, and the matrix is that value squared, right? So imagine we have like thousands or millions of parameters, and we have the same number of parameters in the square here of this matrix. And the major question is, how can we deal with this kind of matrix in efficient ways? And of course, we need to invert that matrix, right? You see this here, we need the inverse of the Hessian here. So next couple of slides are a bit more technical. I hope I can explain that good enough. I like this because I think it's nice to see what can happen here, how can we do good approximations with some mathematical insights. And yeah, I'll try to explain this step by step here. So we have, first of all, we have our Hessian matrix, the inverse of the Hessian matrix. We can say that this, again, is approximately the inverse of the Fish information matrix, which is nothing else than the expected value of the outer product of the gradients, right? So it's nothing else than taking the gradients, outer product of that, and then take the expectation over the whole data set. But usually what you do is you do mini batches here. Now, this again is not such a big step yet, right? Because we didn't win anything here. In the next step, we do a lot of efficiency steps here, because now we assume that the individual layers of the network are uncorrelated. And that would mean that for every layer, we have an individual Fish information matrix, right? So we have as many Fisher matrices as we have layers in the network. And the cross correlations between the layers are assumed to be 0, right? This is, of course, an assumption, but in many cases, you can see that this is actually not so bad. And then the next insight comes that this per layer, right? For every layer, you can say that the Fish information matrix can be expressed as a Kronecker product. And the Kronecker product is nothing else than the activations of the previous layer times the gradient with respect to the pre-activation functions of the log likelihood function, right? So this is basically what comes from the backpropagation algorithm, right? You run backpropagation, and in every layer you have this computation where you come from the right-hand side, you compute the gradients with respect to the likelihood function, with respect to the pre-activation functions. And you can show that what you do here actually is nothing else than a Kronecker product between two matrices. And these two matrices are, again, outer products, right? So outer products of itself. A times A transpose, this is a matrix, and G times G transpose is also a matrix. And then you multiply these two matrices, and you get, again, the same matrix that you have here. Now, this is a nice insight, but we still don't win so much. And what we do now is we do now another important approximation. We say, well, the expectation over the Kronecker product is approximately the Kronecker product over the expectations. And this is quite a strong assumption, right? This is actually something that is not held in general. And the key idea is, or the key goal now, is to make this assumption, or to make this approximation as precise as possible, right? So what we have is we have the so-called Kronecker factorization. We have these two matrices A and G, and we now want to make them look much closer to the true Fisher matrix here. Now, I'm skipping to this. Maybe this is, like, again, a bit of math. I think it should be quite, understandable, because what all we do here is we all apply the rules of Kronecker factorization, how we can apply the Kronecker product, and we leverage the fact that we can decompose the matrix Fi into their eigenvalues, right? So Fi is nothing else than V times lambda times V transpose, where lambda are the eigenvectors and values, and V is the eigenvectors of F. We can do this with F. And we can also do this with A and G, right? They have the same properties. They are positive definite and symmetric. We can also do that for those matrices. And that means we have decompositions of A and G. And now comes a nice thing, because the Kronecker product of A and G is nothing else than the eigenvector decomposition of the Kronecker products, right? So that now we can just switch the multiplication of Kronecker with the multiplication of the matrices, right? And that's the very clever thing. This is very stunning. If you look at the Kronecker product, it doesn't look like that. It looks kind of more, not so easy, but it's very nice that this actually happens. So what we have now is we have now a different formulation for the right-hand part here, for this A times G, right? This is now a formulation. And now the trick is to say, well, now we can relate this product here to our left-hand side, which is V times lambda times V transpose. That means this matrix here, UA times UG, should be similar to V. right? And this matrix should be similar to lambda, but now we find a better way to find lambda. And I'll tell you how to do that. We say, well, UA times UG is approximately V. With that V, we can go back into our definition of the Fisher information matrix, right? And we can compute the lambdas here by diagonalizing the Fisher information, right? So the Fisher information is defined in the previous slide here. And by just diagonalizing that with this V here, we take now the eigenvectors that we just computed, we can find more efficiently and more precisely the eigenvalues of the Fisher information, right? This lambda JJ. And this lambda JJ is a better approximation than this SA times SG, right? So these are better, and then we can plug in here, and we can find out that the resulting Fisher information matrix is a better approximation than this one here, right? Now, in our paper here, an ICML paper, we actually show we go one step further, and I'm not doing this here because it's like too long. We say that we can even add a diagonal matrix to that, right? And the intuition behind is that the Fisher information matrix can be computed precisely in the diagonal. We know the diagonal entries of the Fisher matrix, and all we can do now is we can add some diagonal matrix such that the resulting diagonal is exactly the diagonals of the Fisher matrix, right? This is the whole idea, and there we are even more precise and even closer to the true Fisher matrix than with the current methods. Of course, it brings other problems because now we have to invert that, and that's not so easy to do. But in the paper, we show methods to do the inversion, nicely and with nice methods. Now, enough with math. Let's show you the results on that. We did two experiments. One is an experiment on the toy data set. Here we have a regression problem. We have some training data here, and we want to find the uncertainty estimates within the data and out of the data here. So here we see the so-called ground truth or gold standard of using uncertainty estimates, which is the Hamiltonian Monte Carlo, which is also described in the in seminal work and the thesis of Redford Neal, who actually invented the BNN. So he showed that this is a nice way of actually doing that, and it can be shown that this is a very good way of doing it. However, this can't be done in large-scale problems, right? You cannot do HMC and bigger networks with more data sets, with larger data sets. Now, we compare that to the classical Kronecker factorization and to something that's called Bayes by backprop. Here, you see that this kind of tends to be a little bit underconfident, right? You see there's a lot of uncertainty within the data, right? This method here is of the opposite. This tends to be overconfident, right? It's away from the data, very confident, but then within the data also confident, which is maybe good, but maybe also not too confident. And ours is a quite good trade-off between the two, right? So it's away from the data, it has some larger uncertainty, and within the data, it's quite confident. That's just a proof of concept that it actually works, but what is more important here in this work here is that we can also apply this method to a very large data set, right? And this is unique. This is the first time that something like that was applied to a data set in this size, right? We have ImageNet with thousands of classes. There are 14 million images in the training data, right? This is ImageNet data set. And we use the test data, which is different from the data set, but the classes are different. And we do this to find out how well does the method detect OOD, right? So out of distribution data, right? This is this red curves here. And you can see if we use the predictive entropy to separate in distribution data and out of distribution data, then our method performs best here, right? You see these are classical methods. This is the SGD method, the classical non-sampling based method, right? And these methods here are sample based, right? Where we run several times SGD and do an average over that, right? This is already better, right? But you can see that with our method, you can very nicely find a threshold, right, about here of the entropy that would separate between the unknown data, right, and the known data, right? And this is a nice way of showing that this works also in bigger data sets. Yeah, which brings me to the last point of my talk. Of course, these large data sets and these applications are nice, but very often you have restrictions in terms of computational power and in terms of time, right? So you want to have this fast and you want to have it also in smaller systems. And I'm showing just very quickly 2 examples how we did this. This was work we did 2018, where again we want to find poses of the objects, but we need to do this fast. We really wanted to do this in real time. And the key idea here is to do all the pre-processing beforehand, right? The training time is something that takes very long. We train our autoencoder here. We have domain normalization. We train the network how the orientation of the objects are, and all we get from that is a representation of the object in terms of their orientation, right? So we learn a representation of orientation, right? And then we can store that in a big code book here, which is this database here, and with every embedded vector that we learned here, we can store also the real poses of the object, right? So we have a candidate set of poses here, and then that means that in execution time we can do very quick updates. So we have an input image, we detect the objects, we run our encoder, and then do a very quick nearest neighbor retrieval here from this database, which can be done in real time, right? In the end, we do some refinement steps to find the position, but all this can be done in very fast steps, right? And it's all about having this kind of lookup table here, right? This is the key idea to make this fast. And a different example I also show you here, where we want to do, again, classification, right? We have, again, our standard neural network here, but the idea here now is to combine the standard network with a Gaussian process. And in fact, it's not just one Gaussian process, it's a mixture of Gaussian processes, or a set of Gaussian processes. And again, here the aim was to make this fast and to make it run on a small embedded system, right? Why are we using Gaussian processes here? Well, GPs are known to be very good at uncertainty estimates. So the idea is here to use the neural network to do the label prediction and use the GPs to do the uncertainty prediction, right? So one says the label and the other one says the uncertainty about this label, right? And the idea and the aim is to make this fast and make it run also on the GPU. And we presented it last year at call. So here we have the typical, or the problem that we have here. We have 2 classes, right? One class is called Space Rover and the other one is Space Lander. And we have this small system here, this drone, which flies around and makes classifications. And of course, it needs to know where the lander is and where the rover is. And if you run this without any, in a standard way with neural networks, then in this case, it's actually quite easy to separate the 2 classes. You see this here in this video here. The lander is detected with 100%, which is correct. And when the drone flies here, it sees the rover. It also says, this is 100% correct, and this is nice. However, if you now do some kind of additions to the environment, for example, the space rover is now surrounded by electronics and other things, and the whole scene is not so clean anymore, right? And the lander is also, not just nicely separated, but there's also there's the solar panels up and stuff like that. So there's some changes in the data, right? Which is now this out of distribution case, right? We have the test data is now slightly different from the training data. And then if you run the standard method here to do the classification, you see that it thinks that this is the lander, right? While it's the rover, right? It's actually the opposite, it's just the other class. And it thinks with 100% certainty that this is actually a lander, but there's no lander there, which is, right? This is the rover here. And if you now use our GPs with that, then you see that in real time, we can classify these 2 classes, and we can also estimate the uncertainty, right? We can say, it's hard to see this, but now it's actually these circles here show the uncertainty of the box. And inside the label, we also have the estimate uncertainty. You might still have a wrong classification, but at least you have a high uncertainty, right? And you can still then use that and threshold it and tell that this class might be wrong. Okay, which only brings me to my conclusion of my presentation today. So I showed you different kinds of visual perception systems in applications such as robotics, autonomous driving, but also remote sensors. And what I've shown you today and what I told you is that they make very high demands on data-driven prediction models, right? And what are these demands? Well, first of all, the size and the quality of the training data are very important, right? We need large and good training data in all these applications. And the second thing is also, we need to be able to estimate the uncertainty of the prediction, right? We need to say how trustworthy is our prediction. And the last thing, of course, are real-time constraints, which I showed you also in the last couple of examples. Now, I showed you also some promising approaches to address these. And one, I think, very interesting thing is to use synthetic training data and also these photorealistic things. I think with the current method that we have to generate synthetic training data, we're at a good position to actually use those and to be even closer to the real data sets, so that we may not even have to do a lot of fine-tuning anymore, or only very little. And also showed you some efficient modeling of the parameter posterior. For example, we can use Bayesian neural networks. I've shown you some example how we did that in theory, but also in practice. And finally, yeah, I told you that very often in these small-scale systems, we need some kind of pre-computed or smaller models that then fit into some embedded hardware, right? This is also a key idea here. Yeah, and finally, I just put some further research questions, which I think are interesting. One question is, for example, how can we easily and effectively transfer the knowledge to new systems, right? So we learn from one robot into another system, but also, of course, in remote sensing and other cameras, right? Domains, right? How can we learn from one domain and transfer the knowledge to another domain? Another question is, how can we make the learning process more autonomous, right? So that the learner itself is involved, right? It selects the data, for example, in active learning, but also other things, like so that we adapt the data to the learning process. Or, for example, can we also involve the simulation, right? So can we simulate in a certain way such that we can learn better, right, for example? And the last thing is, how can we make the learning process more explainable, right? Like, so far we have uncertainty and we know where we don't know, but we don't know where this comes from, right? Why do we don't know? Or why do we know? Where are the reasons for this, right? This is the next step then, to say, not just I know there's some uncertainty, but where does it come from? Right? What's the reason for the wrong measurement that we have, or the wrong predictions here? Yeah, and with that, I thank you for your attention, and I'm happy to take any questions. Thank you.
Thank you, Rudolph, for your very interesting talk. So who has questions? Just speak up.
Thank you, Rudolph, for very nice talk. I have a couple of questions, especially regarding the synthetic data part. So what you explained is like we have a simulation model like YSys, using which you are generating synthetic data, and then you are using a deep neural network to further train based on the synthetic data, right?
Yeah.
So here I have two questions. First is like you claim that this model can generalize to the unseen objects. So what do you mean by unseen objects here? Is it like during the simulation, like YSys has a concept of rock, right? So yeah. Even if this concept of rock did not exist in the YSys, even then your model can generalize to it? This is my first question. And the second question is like this pipeline, can it do any better than what YSys already doesn't know? Like using this model-based simulation and then using those synthetic data to further train the model, can it do better than what YSys, the model-based simulation, already doesn't know?
That's a good question. So let me answer the first one. So what is unknown? Unknown is I denote unknown as objects that are not in the training data. That's true. I mean, the rocks that you mentioned, these are similar to the ones that we have in simulation, of course, that's true. And for that reason, we might not call it as unknown. That's true. However, in the case of the indoor network, we show that it works quite nicely also across very different domains, right? So if the objects look very different from the simulated object that we have, then it still kind of works, right? So it's true. I mean, it's also that in the case of the rocks, you the variance is not so high, and you want to have this, right? So of course, the closer you have the training data, the better it is, right? It's not that you force it to be different, but it's good to know that it also would work even if the rocks look different, if you have different shapes, sizes, whatever of your test data. And the second question, I'm actually not quite sure if I get it. So what do you mean with how much better it should work? Maybe can you phrase this again, or?
Okay, so what I mean is like we have Oasis, which is model-based, right? This simulation, which we are using this to generate this simulated training data. Then we are training a deep neural network based on the simulated training data.
Yeah.
So to make these simulations, Oasis already has a kind of background knowledge, right? And is our deep neural network then doing any better than the knowledge that was already there in the Oasis?
Yeah. Okay, I know what you mean. So okay, so this knowledge that you think that the Oasis has is not exactly there. You don't have a knowledge about objectness or stuff like that. So I think what you do is it's like data augmentation in a synthetic way, right? You generate certain situations that might occur in the reality. And that is easier to generate than to really understand why they might happen or where they come from, right? So if you have a network trained on the real data, then you don't have more information learned from the real data than from this simulation, right? It's not that the network has less information from about objectness or something like that. Just because you can generate kind of very realistic looking scenes already, right? And this generation is easier than understanding how the generation process works and learning from that, right? This is the message, basically. Maybe at some point you can, in the later stage, actually do that and understand better what the simulation does, how it does that, and then from there directly come to a model that you can learn. But I think this approach works stunningly well, right? And it's kind of also intuitive, right? It's like what I said before, right? It's easier to model the forward mapping with simulations and not doing the backward processing, right? I don't know if this answers the question, but it's an important question, right? The question is really, if I can simulate it, why can I not directly use what the simulator does to generate the scenes and then do reasoning with that information, right? That's basically what you asked, right?
Yeah. Thank you for that.
Yeah.
Hello. Thank you very much for nice question, nice talk. And my question is, in page 8, you said you'd separated model-driven and data-driven.
Yeah.
In model-driven approach, that is, you said optimization, and in data-driven, you said it's learning. Then have you specified why you said some people do using model-based approach? People learn sometimes, and that's my first question. And second question is, you generate the synthetic data using physics-based model. Yeah. As far as I understood, then physics-based means it's model-driven. Model-driven means you knowing some model. Then my bit confused. If you know model, seems like it will work. I'm not sure if. That's my two questions.
Yeah, that's true. I think that's a similar question as before. So first of all, the question about observation and learning. So, well, mathematically, you also do some optimization in the learning process, right? You have an objective function and you optimize that objective function. That's also learning. Learning is just a nice way of putting it, but learning also involves not just optimization, right? Optimization so far is just finding the parameters and then you have it and that's it. But learning is more than that. Learning is also like using that information and doing inference in some steps. So you have some test data set and you apply the model that you have optimized for in the training set also in inference, right? This is roughly the kind of difference, but the differences are not very high, I would actually say. I don't know if that answers the question. So you, yeah, I mean, yeah. And the other thing is, yes, you have, well, I think in simulation, the simulation that we have, of course, we have some kind of model knowledge, but what do we have is, for example, the geometry of objects and and things like that. But I think that's not sufficient to actually do reasoning on the real data, right? You would have to have all kinds of geometries of models that of objects might be around there, and this is harder to model than to learn, right? Learning means just, yeah, use a model, put some randomness on it, and generate as much data as you can from it. And that is easier to do than to actually model the process of this geometry, or how to train how these objects are generated. But I agree. I think it's a question of, yeah, if I have a good representation, a good way of physically modeling the environment, and if that's sufficient to make realistic images, why not use that also to actually reason on the real data? That's true. I mean, in these examples, this is all about just like visual synthetic data, right? So there's no, or little physics in there. We don't have the weights of the object. We don't have these kind of things, right? We don't need this because we just need to know how they look like. And yeah, yeah, I think it's just the answer is just using that as the more straightforward way and the easier way, because otherwise we'd have to apply all the rules that the Blender, for example, the Blender simulator applies to generate the data. We need to kind of understand them better and also apply them to real data. I don't think that's that easy.
Okay, thank you very much. Yeah, that answer. Yeah.
Hello.
Hi.
Hi. It's a very nice talk, and I have two questions. The first question is that about your Bayesian neural network. Yeah. I know there have a problem is that it's a very large matrix. So you choose the Bayesian neural network to reduce the dimension of the weight instead of using some spare loss, such as L1 loss or some other methods, such as dropout. So I have a question: is that why you choose the Bayesian neural network to reduce the dimension, and instead of other methods? And this is my first question. Yeah, it's there. And okay. And
okay. Thanks. Sorry, are you okay? First that one, then the one. That's easier to answer that. So thanks for the question. So the question is why Bayesian neural networks and not other methods such as dropout or other methods to reduce this dimensionality. So I agree. I mean, there's many methods. This Bayesian neural networks, show good performance, and they are like mathematically kind of describe the process quite neatly, right? So they are also in terms of efficiency. For example, if you compare this to ensemble methods where you have to sample different networks, those are usually larger and you need more space to store them. Here you just have this one network. And another important aspect of these Bayesian neural networks is that you don't have to retrain them, right? So what you can do is you can use a network that is already trained, and what all you need here is the gradients that were produced during the training process, right? And with those gradients, you can compute these fish information matrices, and you don't have to retrain the network. And other methods usually have to retrain, right? And that's something you don't need to do here.
Okay. I think it's a very great method to deal with this large matrix. I think that, And another question is that the you say the model-based or data-based, and you say it's very important to get an accuracy label. However, you say in many small or special physical models, we don't have the ground truth, and we don't have the accuracy label. So in terms of this case, how we get the accuracy label? Because we use self-supervised or some other methods, we cannot get the accuracy label. So how can we
yes.
obtain? Yeah,
that's a good
yeah.
point.
Do you have some idea? Yeah.
Yes. So that's a good point, and that's also a big problem with model-based approaches, right? In this case, what I showed here, which is the calibration case, you do have very good precise ground truth, right? So let me show this here. So this is the data here, and you can very precisely know the points, the 3D points of these patterns here, right? So you have, in this case, a very precise ground truth, but you're actually right. If in general, you don't have this, and for those methods, it's definitely then harder. For that reason, model-based approaches are also very hard to apply in other senses. That's true. Yeah.
Okay. Okay. Thank you.
Hello, here is Elaine, and I have a question about in your talk you mentioned if we want to avoid to label the large data set, you use two techniques, synthetic data and self-supervised learning, yeah, for training the model. So I mean, if you want to deploy the model for the real application, you need to really well evaluate the model. So I mean, for evaluate the model, you still need to label a large data set. How do you handle this problem?
You mean for the inference?
Yes, yeah. If you, I mean, usually for some publication, you test on some small data set, yeah, to evaluate your model is good or not, yeah. Right. I mean, for some real application, for example, for the autonomous driving, yeah, you need to test it and deploy model to evaluate the generability and the robustness, yeah, for different scenario. And for the for this data-driven method, you don't know under which scenario it fails, yeah. You need to test them more and more, yeah. So which means you need also label very large data set for evaluation, yeah.
That's true. Yeah, that's true. If you want to evaluate, if you want to show that your method works in large scales, then you need, of course, the ground truth also for the large scale data sets. And for that reason, this is what I showed here also in slide, I think 13. I don't see my pointer anymore. My pointer's gone. For that reason, we use now this ImageNet data set, right? ImageNet data set is a good example where, where we have a large data benchmark data set, which is already labeled, right? You have ground truth labels for those. But I agree, you don't have this in many domains, right? So I think this is a big issue, right? If you really want to show that your method works on large scale, then you need ground truth to do that. And in many cases, it's not the case, right? What you can do is you can still show that it works in ImageNet and then hope that it also transfers to the other domain and it works in the other domain as well. But yeah, this is yet to show this is actually working.
Okay.
Okay. I can't hear you, Julia. I can see you talking, but I can't hear you.
Oh, no. Okay.
Now I hear something.
I guess, Julia, you just want to close the session, right? Yeah, we can hear you, but not very loud.
But you can hear me?
Yes.
Oh, okay. So that's it for the questions. Thank you for the very interesting talk, Rudolph, with the beautiful pictures. And I close today's lab talk.
Thank you very much. See you around.
Thank you.
Ciao, ciao.